Okay, so let us now see this next section, the maximum principle. Now before starting the section, the author says that we have already seen many examples of continuous functions. We have also seen that there are functions which are not continuous, but a large class of continuous functions exists. But why are continuous functions so important? It's because they enjoy many useful properties which discontinuous functions do not enjoy. So in this section we are going to see one such property. And in this section we are also going to use the full power of the Heine-Borel theorem. You remember that we came across one result in the first section of this chapter, which we used also, but not fully. And that result was this. If X is any subset of R, then these following two statements are equivalent. X is closed and bounded. This is one. And there is another one. If Xn is any sequence in X, that means where the terms are all coming from X, then there exists a subsequence of that sequence which converges to some element again in X. Heine-Borel theorem states that these two statements are equivalent. If any one of them is true, then the other one is also true. So we are going to use this. Now the section starts off with this definition. The definition of a bounded function. So the definition basically says that it has three parts. Let's see what those parts are. Again, let X be a subset of R and F be a real valued function defined on X, that is, it has X as its domain. Then we say that F is bounded from above if there exists, let me just use this symbol here. This means there exists. We haven't used this symbol in this text, it's not there, but just for the sake of simplicity, I am writing this. There exists a real number such that all the functional values are bounded from above by that real number. So this is one part of the definition. Similarly, F is bounded from below if there exists a real number, small n, let us denote it by small n, such that this time all the functional values are bounded from below by that small n. And there is a third part also. F is bounded. If is bounded means F is called bounded or it is defined to be bounded. If there exists, again let's denote this one also by n, like the author has done. in R such that the absolute values of all the functional values are bounded from above by M. From above, of course, because from below it's already bounded by 0. You can, of course, say that it is bounded from below by some positive real number, but nothing like that has been defined. So this is what the first definition has. Two types of boundedness, from above, from below, and one which is just simply boundedness. Now, although these things are different, but they are related in this way. That's what this next remark is about. The next remark is very natural. It basically says that F is bounded in that sense if and only if it is both bounded from above and below. This seems plausible and it is very natural and perhaps obvious to you, but remember, no matter how obvious or trivial something is, we should have an explanation for that, at least to ourselves. We should be clear why something is obvious and why something is true. So instead of taking general capital M, small m, let us just try to see why this is true. Okay. So let us suppose that F is bounded. Let's first see the easier one. If F is bounded, then there exists. Here there is no point taking special values. Let's just take M. If F is bounded, then there is one M for which these inequalities are true for all x belonging to x. But then we know that these inequalities are equivalent to these inequalities and they immediately tell us that F is bounded from below by minus M and from above by plus M. That is, F is bounded from below and above both. So that means one half of this claim is true. Now for the converse, let us take some values. Okay. Say so what is the converse? The converse is claiming that if F is bounded from both above and below, then F must be bounded. Suppose F is bounded from below by minus 3 and from above by 2. Then how can we find one such F? That is the question. You see, finding one such M is equivalent to finding these inequalities. And we are given something like this. So that perhaps immediately tells you what to do. Because these inequalities immediately imply these inequalities. Because if all the F values are less than or equal to 2, then automatically they are also less than or equal to 3. In fact, strictly less than 3. And that in turn implies this. But you may not really feel that convinced by this situation. You may think that I have cherry-picked this value so that I can get something like this. What happens if, say, the lower bound is also positive? Say, instead of these inequalities, I have something like this. Say, then what do we do? But then if you think of it a little bit, you will see that these inequalities imply this as well. If the f values are at least 10, then of course they are greater than or equal to minus 11, definitely. And that implies this. So here also we have found one such f. From these two instances, you can try to formulate what to do in the general case. Say, you have one lower bound, small m, and an upper bound, capital F. What to do? Okay, what should our capital F? Of course, this m is not actually this m. If you want, you can use some other letter also. So you can try to guess what this m is in this general situation. Maybe you will have to take some more such inequalities, some other lower bound or upper bound. So I leave this part to you. So do you see that although it looks like an almost obvious thing, but when you try to do it, it's really not that obvious. So that's why we have to be careful. But anyway, let me just leave this and let us continue. There is one more thing, the remark also says something else, that f is bounded if and only if the set, the image set of x under f is bounded in the sense of definition 9.122. That is the definition of a bounded set. A subset of real numbers has a notion of boundedness. Okay, it is that definition. So f is bounded if and only if this image set is bounded. Why that is the case? So this part also I leave to you. And these things that I leave to you, please try to see why these things are the way they have been claimed. And if you don't get anything, then please let me know in the comment section. It's always nice to have comments because you see, when I go through these things, I am only thinking in my own way. Now, if I get a comment that asks me something, then I may get another perspective, and often it turns out that way I learn much more. Okay, so it's not that just simply you are seeing these things and you are learning, we are learning, but I am also learning, because we are actually all learning. So to facilitate that even more, so you should write some comments. Okay, so now we have the notion of bounded functions. Functions whose values are tame, that is, they are not very wide, they are not going very far away. They have upper bounds, they have lower bounds. So what is the relationship between bounded functions and continuous functions? Not all continuous functions are bounded. For example, if you consider these functions then, this very straightforward, simple, linear function, the identity function, then it is not bounded. Because you know what its graph is. It is that straight line which passes through the origin and it has slope 1. It's not bounded. Its values go as low as you want. They also go as high as you want if you go far enough on either side. But this is continuous. So it is continuous but not bounded. You may think that this has something to do with R being itself unbounded. So we have got infinite room for to make this happen. But even if you concentrate on a small portion of R, still you may get unboundedness. But still the function may be continuous. One such example is this. Is, say, the reciprocal function. You also know what its graph looks like. Okay, so let me just, because I am going to draw the graph, at least let me use a ruler to draw the axis. Okay, so our usual x-axis and y-axis, and we are now concentrating on the open interval 0, 1. So in this open interval, a graph is going to roughly look like this. Actually, this line never keeps coming closer. I mean, it gets closer and closer. Okay, it never stops coming closer to the y-axis. As your x value gets nearer and nearer to 0, so that means the denominator is decreasing in size. So the numerator, that is the functional value, increases without any bound. So it becomes larger and larger, and at the same time it keeps getting closer and closer to the y-axis. And on this side, of course, it goes down. And it's continuous. It's continuous because you see, why is it continuous? It's because it's the quotient of two continuous functions. And from algebra of continuous functions, because the quotient never vanishes, it never becomes 0 inside this domain. You see, we have kept 0 outside of the domain, so there is no problem. Both the numerator and denominator are continuous because the numerator is a constant function and the denominator is the identity function. Both of them are continuous. The denominator never vanishes, so the quotient is also a continuous function. But it's not bounded because of this nature. So this is again continuous but not bounded, in spite of having such a tight space, if you want to call it so, against the unboundedness of R. However, this same function, if you consider on some other interval, say the closed interval 1, 2. Okay, so if you continue this further on that side, then on 1, 2 closed interval, right, it turns out to be bounded. So is there any special role that is being played by closed interval? This closedness is not there in this or R. Yes, and that is what the next result is about. It is not simply about closedness, but it's about something called compactness, or rather connectedness, I think. But there is no point discussing about these fancy terms. Let's just see what the result is. We are still far away from compactness, connectedness, those topological notions. So what this result says is just this. Say A and B are two real numbers where A is less than B. And suppose this is a continuous function. So now the function is like this and it's continuous. So the domain is a closed bounded interval and it's continuous. Then f is bounded. F is a bounded function. So what we saw not happening in those cases will happen in this case. Now we are going to prove this. And in this proof we are going to use Einborn's theorem. The proof is not a direct proof, it's by contradiction. So the very right off the bat, we are going to suppose that, say, f is not bounded. Suppose f is not bounded. That means there is no such n for which this will happen. This statement is not true for any n. No matter what m you choose, this statement will be false. Now look carefully that this is not a simple inequality, but rather it's infinitely many inequalities because there is a quantifier for all. So we should be rather careful in writing the negation of this statement, actually, which is what we are supposing here. What is the negation of this? The negation of this is that no matter what m you choose, the exact opposite inequality will be true for at least one point in the domain. Actually, there is a general rule, a mechanical rule of turning such a statement into its negation. Namely, this part, you just simply negate it. Okay, this is less than or equal to m. This is not less than or equal to m. That means this is greater than m. And you change for all quantifier into for at least one, or more simply for some. That's it. This part remains the same. But we should not memorize such rules. Okay. Instead, we should just think naturally why this should be the negation of this. And this is naturally it's understandable why this should be the negation of this. Now, so now what is it that we are having? That for any real number n, this happens. In particular, for any positive integer m also this is going to happen. So I am directly writing. Actually the author writes this in the proof, and then he is going to write something else for positive integer, but I am just simply directly writing this. Then for each positive integer in the absolute value of some functional value is strictly greater than n for some x in the domain. In place of for at least one, I have written for some. Same thing. That is, for every positive integer n, this set is a non-empty set. This is a non-empty set because there is at least one such x. So this is the set of all the inputs x for which that happens. Okay. And this is the perfect position where we are able to use the axiom of choice. Remember the axiom of choice? It's a very natural axiom. It just basically says this: you have a number of bags or boxes, and there is something in each box. Then you can choose one object from each box. That's it. Now the number of boxes may be infinite. So here, in place of boxes, we have these sets which are non-empty. So these are like bags. Okay. In each bag there is at least something. So we can choose one object from each bag. That's what the axiom of choice says. But note that although the number of bags here is infinite, but what kind of infinite? Countably many bags are there, because for every positive integer there is one non-empty bag. So that means for every positive integer I am able to choose one object from a bag, and that gives me a sequence. So by the axiom of choice, there exists a sequence xn in the closed interval a comma b such that this is greater than n for all positive integers n. This doesn't look like objects have been chosen from a bag, right? Or from these sets. So what has happened is that we are choosing xn from this set, another xn from some other set where in place of n you have n. That's it. Okay. So the axiom of choice allows us to choose one such sequence. You may think that why we need an axiom for this? Is this natural? No. Yes, it is natural. But you see, there is actually no definite rule by which we are making these choices, infinitely many choices. We don't really know what this xn, what type of element xn is. This set may have many elements. No? We are just arbitrarily choosing one xn from here. some other xn from some other set. So there is no definite rule. However, a sequence after all is a function, so it demands that for every input n, the output should be a unique element. So if you do not have any such axiom or anything, then the arbitrariness of these choices do not give you actually any unique xn for every given. That is the problem. So that's why we need an extra axiom. But anyway, we now have a sequence. And why is it a sequence in A comma B? Because after all, no matter what xn you are going to choose from this set, that is coming from here only. Okay. So now comes the Heinberg theorem. Theorem 9. What is that number? 9124. Since this is a sequence in this closed interval, and the closed interval is a closed and bounded set. So there exists a convergent subsequence, and this is closed and bounded. So by theorem 9124, or in other words, the Heinberg theorem, there exists a subsequence. I'm writing everything now, but sometimes it's nice to write. And sometimes writing really makes things boring. Subsequence such that this subsequence is convergent, and not just that, it converges to some point inside the set itself, or some L belonging to this. Okay, so now you watch this closely. You now have a subsequence. The terms of the subsequence all are lying inside this. What is this set? This set is the domain of the function f. Okay. And f is continuous. So by sequential formulation of continuity, because this is a convergent sequence, since f is continuous at L, we should have this. The corresponding functional values are going to give us another sequence. That sequence should converge to the functional value at L, f of L. But now there will be a problem. And the problem will come from the way we have chosen xn. But this, okay, is strictly greater than aj, because that's what the terms of our sequence xn are. If the f value at xn is strictly greater than n, that is its property. So similarly, for this particular subscript values nj, also this should be true. And here we are going to write one extra thing. Okay, nj is greater than or equal to j for all positive integers j. Let's just take this for granted. For now, I am going to say why this is so. But if you assume that this is the case, then this functional value has become greater than or equal to j, which means that if you take, say, in particular j equal to 1, then this functional value is strictly greater than 1. If you have j equal to 100 here, then this functional value is strictly greater than 100, the integer 100. So obviously this sequence is unbounded. How can it be bounded? Its terms are getting bigger and bigger. They are exceeding these integers. Okay, so it cannot be bounded. So this sequence is unbounded, and that is a contradiction. Why is it a contradiction? Because if you recall, we proved in the chapter on sequences that every convergent sequence is a bounded sequence. Okay, boundedness is a necessary condition for convergence, not sufficient but necessary. If a sequence is convergent, then it has to be bounded, but that is not happening here. So our initial supposition is wrong. What was our supposition? That f is not bounded. Hence, f must be bounded. So that way we have achieved the proof, but there is one gap. What about this? Where is this coming from? The author has simply mentioned that this happens, and he has asked us to prove by induction. It's actually a simple matter, but still let's see how this is true. You see, we already know one thing, because we have said that this is a subsequence of this sequence. So what we know is this: these indices form a strictly increasing sequence of positive integers. In fact, this comes from the definition of a subsequence itself. Okay, so if you are doubtful about why this is true, you go back to the definition of a subsequence of a sequence. There itself you will see that this is the condition for this to become a subsequence. Okay, so now we are going to prove that actually, that thing, by induction. So what should be the basis for our induction? N1 is greater than or equal to 1, but that is true, because these nj's are some n. Which n we don't know. That depends on how this nj itself has been defined. But after all, any such nj is a positive integer. In particular, n1 is also a positive integer. So being a positive integer, it has to be greater than or equal to 1. which is what we are claiming when J is equal to 1. So this is the basis for our induction. Now, say this is our induction hypothesis for some arbitrary but fixed positive integer J. Now we need to say something about Nj plus 1, the next one. Because of this pattern, Nj plus 1 is strictly greater than Nj. However, our induction hypothesis gives us this. That is, Nj plus 1 is strictly greater than J. Now notice the fact that these are integers. That is why this strict inequality implies this ordinary inequality. Even if we add 1 to J, we are going to get this. We will never exceed Nj plus 1. In the extreme case, say this is suppose 3 and this is 2. That's the closest J can get, still being smaller than 3. But then 2 plus 1 is 3, so you get equality, but you do not exceed that number. But that's it, that completes the induction. So that is the explanation for that thing. Okay, so this is how we have obtained the fact that unlike continuous functions defined on some other sets, if it is defined on a closed interval, then it must be bounded. Okay, it cannot be unbounded. Now, there is a remark which follows this proof. This remark is about two things. The first thing is that it shows how useful Hang-Borel theorem is. And in fact, this is just one of the uses of Hang-Borel's theorem. We will be using it again and again many times. Anytime we are able to obtain a sequence inside a closed and bounded set, there will be a convergent subsequence. That too, the limit of that convergent subsequence will lie inside that set. From that, we will be able to do many things, because this is just one instance. And the second thing about this proof is that it's not a direct proof, because of which it does not tell us what that M is. So we have proved that every continuous function on a closed bounded interval is bounded. But what is that bound? Do we get any idea from the proof what this M can possibly be? No. It's an existence proof. It says that such an M exists. So you know that such an M is there. So if you want to find such an M, you have to work separately with the function, the functional values, and then you can figure out what that M is depending on the situation. So that's just it for tonight. Tomorrow also we are supposed to have one analysis video, but because of yet another festival, it's a country of festivals. Okay, I don't know if I will be able to film it, because tomorrow the noise pollution will be, I will call it a pollution. Okay, it turns into a pollution, will be too much. So let's see if I'm able to film one video. Definitely there will be one analysis video which will contain the things that come next. But if not, then we will see on Tuesday again. And on Tuesday, let's go back to field theory again. So with that, I am just signing up for tonight. So see you either tomorrow or on Tuesday. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.